Hi, I am Yifan Peng from Carnegie Mellon University. In this presentation, I will introduce our paper, Reproducing Whisper-Style Training using an open source toolkit and publicly available data. I will first introduce the motivation to reproduce Whisper-Style training. Then, I will describe our design and experiments. Finally, I will talk about future research directions. Recently, there are several trends for developing speech models. We are moving from monolingual task-specific models to multilingual multitask models. The model and data sizes are also greatly increased. This type of model is usually called speech foundation model. Speech foundation models have several benefits. They can achieve better performance thanks to larger amounts of training data, larger capacity, and cross-lingual and cross-task knowledge transfer. Additionally, we only need to train and deploy a single model, which is easier and more efficient. OpenAI's Whisper is one of the most popular foundation models in the speech field. It is based on a standard transformer architecture, but is trained on multiple speech-to-text conversion tasks, including multilingual speech recognition, Any-to-English speech translation, language identification, utterance level alignment, and voice activity detection. All the tasks are represented in a unified format so that they can benefit each other. The most notable feature is that the training corpus contains 680,000 hours of labeled audio data, which are collected from the web. Whisper generally achieves good performance, especially for high-resource languages. However, the full pipeline is not publicly available. We don't have access to their training data, and we don't know the implementation of the training procedure. This raises several concerns. Firstly, information leakage might happen if we use Whisper on a new benchmark, because we don't know if the test data has been included in the training set. Secondly, we cannot access and study the training dynamics of large-scale speech models, making it difficult to further improve the performance through community efforts. Thirdly, pre-trained models can have issues about robustness, fairness, and bias, which are often related to the training procedure. It is thus hard to mitigate such issues, since we don't know the training data and training details. Therefore, we need more transparency to promote open science for speech foundation models. Inspired by this, we propose our model called OWSM. Here is an overview of OWSM. We aim to reproduce Whisper-style training using publicly available data and open source toolkits. We basically follow the design of Whisper, but with several modifications. We extend speech translation to more language directions. We increase the downsampling ratio in the encoder to reduce computational cost. We further adopt joint CDC attention to improve both convergence and final performance. OWSM achieves good performance on many benchmarks. It sometimes even outperforms Whisper. Next, let's look at more details about OWSM. For the multitask data format, we follow Whisper to unify all tasks as autoregressive generation. Some special tokens are used to specify the task. The timestamps are also special tokens. During training, we use teacher forcing. For inference, we will specify the task and generate other tokens sequentially. OWSM is trained on a diverse combination of public ASR and ST datasets. For audio, we concatenate consecutive utterances to form longer utterances. Same as Whisper, we pad the input to a fixed length of 30 seconds. For text, we try to use the original unnormalized transcriptions, but some datasets do not provide such text. So our training data is actually a mixture of different styles. In this paper, we present 3 versions at different scales. The largest one matches the size of Whisper median, but our training data is only about a quarter of the Whisper training data. This figure shows the data sets for each version. We gradually add more data and more languages from V1 to V3. And V3 contains 180,000 hours of audio data in 151 languages. And next, I will discuss the results. For English ASR, we compare OWSM and Whisper on several commonly used benchmarks. OWSM generally achieves good performance. It is even better than Whisper on LibreSpeech and Switchboard, although our English data is much smaller. We noticed that there is a large degradation of OWSM V3 on Wall Street Journal. After some investigation on the training data, we found that it was likely caused by the inconsistent case and punctuation. This shows the benefit of using public data. Please find more discussions on our paper. For multilingual ASR, the performance is highly related to the training data size. For high-resource languages such as English, Chinese, and Japanese, OWSM outperforms Whisper. For languages that have fewer training data, OWSM is worse. If the training data is less than 1,000 hours, the performance will be much worse. We then evaluate our model on long-form ASR based on the predicted timestamps. We can see that OWSM is still worse than Whisper, but it works reasonably well. Here, we show 2 examples of timestamp prediction. The predicted timestamps are usually accurate. Sometimes it might merge consecutive sentences, but the behavior is also reasonable. As mentioned before, Whisper can only perform X to English translation, while OWSM supports more translation directions. As shown in this table, our translation data size is much smaller than Whisper, so our performance can be worse in this case. For language identification on FLIRs, OWSM outperforms Whisper by a large margin. This is mainly because OWSM uses the training data from Common Voice and FLIRs, and it contains more languages than Whisper. Finally, we present ASR results using different decoding algorithms that are supported in ESPNet. We can see that joint CDC attention decoding achieves the best performance compared to CDC or attention only, but it will be slower. In this work, we demonstrate that it is possible to reproduce Whisper-style training using public resources. In the future, we will explore the following directions. Firstly, we will try to improve the performance by increasing the data and model size, and by using more advanced encoders, including branch former. Secondly, we plan to support more tasks, including spoken language understanding. Thirdly, current speech foundation models can be very large and slow. We will explore various model compression techniques to improve efficiency. Finally, our reproduction provides a valuable testbed to investigate interesting machine learning topics, such as data imbalance, continual learning, robustness, and so on. Our code has been publicly released in ESPNet. The pre-trained models and the training logs can be found on Hugging Face. We also have a Gradle demo on Hugging Face. You can play with it if you are interested. Thank you for listening.